Okay. Hello, my name is Emma Yeats. I am a fourth-year physics major at the University of Virginia, and I did my research on gluon generalized Parton distributions and their relation to the angular momentum sum rule. So, the angular momentum sum rule it was proposed as a response to the proton spin crisis, which is the realization that the spin of the quarks doesn't fully account for the spin of the proton. In fact, it accounts for less than 24% of the spin of the proton. And so in response to that, Zhang made this, this equation one, which basically is saying that also we need to take into account the spin of the gluons, as well as the orbital angular momentum of the gluons and the quarks. G also postulates that there are these things called form factors, which can help us find the total angular momentum using equation 2. However, this second form factor, B of t, is not detectable and thus is the missing component to fully unlocking the angular momentum of the proton. So I did my research mainly on the GPD EG, which is a chiral even GPD, and it's hasn't been researched quite as much as its counterpart H, and the reason is because of, well, basically of the reason is because of the issue with B of t. But the nice thing about EG is that it actually integrates to a moment B2, 0 of t, which is a section of B of t that we want. So the GPD itself is obtained through these expressions. This first expression is the raw form of the GPD, and the second expression is the Reggie term, which we use to fit the GPD to other models. And that Reggie term is given in equation 4. And the Reggie term is in terms of x and t, and the GPD is in terms of x, zeta, and t, as well as being involved in this thing called t-squared, which is a way of zooming out or scaling the proton. So the methodology that I used to fit EG was this integral fitting method. And the first thing I did was in the forward limit, which is a fancy way of saying t being 0, fit the integral of EG to a constant B of t, which is we set equal to 0.075, which we kind of derived as being the average of lattice QCD results, which are given in the reference below. And we did that by varying free parameters like the ones listed. And then after that was done and the integral fit to the form factor, we were able to then evolve, or not evolve, we were able to vary t and then also fit at various values of t. So t, especially going from 0 to -2. And in this graph here in section 3, kind of visualizes that fitting process. The blue line, the light blue line, is the constant we fit to. The error bars are the lattice data, and the green line is the average of EG that we used, and the shaded region is the error on that GPD. So yeah, and then in the end, we were able to uncover 3 parameterizations for EG, 2 of which, EG2 and EG3, we calculated using this integral fitting methodology, but the first one, we actually fit to a dipole form factor, which is different form factor completely than the lattice QCD results. So, and the differences like visually between those 3 can be seen here. So this first one has more of a valence shape, what we call a valence shape, and the second 2 have a visible node. So What we also found interesting was that alpha prime and p, which are two terms found in the Reggie term, or two variables found in the Reggie term, within error ended up being about 0. And so kind of interesting that the Reggie term, at least for EG, would not have any t dependence. So yes. And then all of our GPDs were evolved to q squared equals 4. In this graph right here, this is a graph kind of displaying or helping to visualize how what q squared looks like, or evolution in q squared looks like. So all three of these began at different initial q squareds. This one began at 0.97, this one began at 0.92, this one began at 0.58, but all three of them were evolved to q squared equals 4. And the reason we did that was because that's more of a kinematic range, or kinematical range, that range that's comparable with current data from Jefferson Lab, and hopefully future data from the Electron Ion Collider, or the EIC, which is going to, yeah, I think they're going, yeah, in Brookhaven National Labs. So yeah, so comparing these new models, these new parameterizations with hopefully, new data, experimental data in the future, we hope that'll take us closer to understanding how the proton is structured. So, and then in the future, what our group aims to do is perform a Fourier transform on the GPD. This graph here is, it is a Fourier transform of the GPD, but only of the quarks sector. And we also want to input the gluon sector to make a more complete spatial distribution of the angular momentum, which is what the Fourier transform does on a GPD. And this is kind of what we call imaging the proton, and is mainly our goal. So yeah, we just want to see how momentum is distributed within the nucleon and see what that looks like. So we're very curious. So yeah, so thank you to everybody at SIWIF, everybody listed at the top, and thank you so much for listening. All right, thanks.